Welcome back to HackCode. In this video, we're gonna explore an essential problem for coding interviews, clone graph from LeetCode. This problem is great for learning graph traversal techniques like DFS and BFS. We'll explore two approaches, DFS and BFS. Let's break down the problem step by step and understand how these solutions work. So sit back, relax, and let's dive in. So what is the problem statement? Given a reference of a node in a connected undirected graph. So what do we mean by undirected graph? So basically, undirected graph is a graph where edges between the nodes do not have a direction, meaning you can traverse the edge in both directions. A connected undirected graph has following properties. So basically, first is undirected edges. Undirected edge in the sense like each edge is bidirectional. So example, if there is an edge from node A to node B, you can traverse from either node A to node B and node B to node A. So basically, there is no direction. It's a bidirectional. Okay. Next is connectivity. Graph is considered as connected if there's a path between every pair of nodes. So no node is isolated, meaning all nodes belong to the same connected component. Okay. So let's look at the examples here. So firstly, here we have an example of a connected undirected graph. So here, what are the nodes? So here 1, 2, 3, 4 are the nodes. So what are our edges? 1, 2, 2 and 1 to 4 and 2 to 3 and 3 to 4. These are our edges. And next, what is the path from 2 to 4? You can go from 2, 1, 4 or 2, 3, 4. Okay. So basically, there is no direction. That's the idea. And now let's look at the example of a disconnected undirected graph. So in this case, the nodes are 1, 2, 3, 4. And what are the edges? It is 1 to 2 and 3 to 4. Okay. And the graph is not connected because here these are two separate groups, right? So we don't have any connection between 1 and 3 or 2 and 4 like that. So that's why it's a disconnected undirected graph. Okay. So now let's come back to the question. So here we have to written a deep copy or clone of a graph. So basically, what is a deep copy? Deep copy is nothing but we have to create an entire new object of the given graph. We can't just simply point to the given graph and send it. So we have to create an entire new copy. Okay. So that is actually cloning. So each node in the graph contains a value which is integer and a list which is a list of nodes of neighbors. So basically each node has this value, right, which is integer and a list. Basically this represents the connected nodes to this node. Okay. So this is the data structure for that. And here they just given the test case format. So for simplicity, nodes value is the same as the nodes index. So basically it is a one index. For example, the first node with value is equals to 1 and the second node is equals to value 2, so on. The graph is represented in the test case using an adjacency list. So adjacency list is nothing but for a given node, we can just see the list of connected nodes. So that's the idea here. And in this example, so the first node value is 1 and the second node value is 2. So 1 is connected to 2 and 4 and 2 is connected to 1 and 3 and 3 is connected to 2 and 4 and 4 is connected to 1 and 3. So basically here the indices represent the value of that node. So for simplicity they made this representation. Okay. So actual adjacent list would look like something different. I'll show you here. So let's consider this example here. So this is the adjacent list which they given us. Now the actual representation is like what? 1, 2, 4. So this is list. Okay. And next we had 2, it is 1, 3 and next we have 3 and it is 2, 4 and next 4 it is 1, 3. So this is how we represent a adjacency list, but here for simplicity sake they just given this list as a, like neighbors, and the value of that particular node is the index. So here this is one index, right? So the value is 1 and next is 2, like this is 3 and next is 4. That way. So basically here one base index. That's the idea. And here the output is what? The same graph. So basically we had to return a new graph form. Okay. And the expression is same as what we discussed. So in picture what they mentioned is, so this is the original graph. We can't just return the same graph. That doesn't mean that you can form a nodes in like different random order. We had to return the nodes in the exact same order in the clone graph. So that's the right answer. So that's what they given here. So in example 2, we have an empty list. So basically here it means we have a one node and that doesn't have any neighbors. So why I said one node? Because this empty list represent what? Is the neighbors of the node at the particular index. So here it is one index. The value of node is 1 and it has no neighbors. That's the idea. And example 3, we have an empty graph. So basically it doesn't even have any nodes. If it has nodes, it would have at least the empty list in that. So if there is no empty list, that means that there is no nodes in that. Okay. So this is the empty node graph case. Okay. So what are the constraints here? The number of nodes in the graphs is in the inclusive range of 0 to 100. So basically here the number of nodes in the graphs is in the range of 0 to 100. It's inclusive. And the node value also in the inclusive range of 1 to 100. The node value is unique for each graph. So we don't need to care about duplicates. And there are no repeated edges and no self loops in the graph. So we are safe, right? We don't need to handle that conditions. and the graph is connected and all nodes can be visited starting from given node. So basically what they are saying is we can visit all our nodes from the starting given node. Okay, so let's look into the boilerplate code. So here we have clone graph method which takes a node. So node could be null, so that's why it is optional here. Okay, and it returns the optional of node. So basically when they give the empty graph, we have to return the empty graph, right? So for that case, this is the optional they given. So optional is for handling the null cases. Okay, so now let's look into approaches. Before we get started, I want to remind you about our exclusive blind spot info post. This carefully curated collection covers essential coding interview problems to help you master the most common patterns and excel in your interviews. Whether you're prepping for FANG level interviews or just sharpening your problem solving skills, these problems will ensure you're ready for anything. Even if the exact questions aren't asked, they cover all the important patterns. So be sure to check out our playlist and stay ahead of the competition. So now let's look into the traversals we're gonna perform. So basically, here I'm considering tree because it's a special type of connected undirected graph with exactly n-1 edges. Okay, so if we consider doing DFS, which is nothing but the depth first search. So for DFS, we aggressively explore the neighbors. Okay, so if the given node is 1, firstly we explore 1, and next we go to 2, and next we go to 3, and next we come back to 2, and then we explore 5. So you get it, right? So we are going as deep as possible, and next we coming back to the 1, and then we explore 4. So here the order is what? 1, and next is 2, next is 3, and next is 5, and next is 4. So that's the order. So for BFS case, we explore the levels first. There's a breadth first search. So we explore one level, and next level. So here the order is 1, and guess what? It's 4, and next it's 3, and next is 5. So that's the idea, guys. So basically here DFS is nothing but we explore the depth, and BFS is nothing the level of the traversal. We explore the particular level and we go down. So basically in BFS, we explore the given node's neighbors, and then we go back to the next node, and then we explore those nodes' neighbors likewise. So let's look at the approach one, which is the depth first search. So what is the intuition here? Using DFS, we traverse the original graph while cloning its nodes and edges. A hash map is used to keep track of already cloned nodes, ensuring we avoid redundant work and handle cycles effectively. So basically here we perform DFS with help of a hash map. So this hash map helps us to keep track of the nodes which are already cloned. So that way we avoid the cloning of the node which is already cloned, and also it will help us to handle the case where we have cycles. So if we have cycles, if we visit the node once, we ensure that we don't visit it again by checking if it already exists in hash map. So this hash map is preferred because for its O of 1 lookup. So this would offer very high efficiency in our code. Okay, so hash map would have a key and value. This key is what? The given node, and value is the clone node. Okay. The DFS approach is recursive and process one node and its neighbors at a time. So basically, DFS is always a recursive approach. That's what we mentioned here. And let's look at the algorithm. So firstly, for any recursive case, it starts with the base case, right? So that's how we started the base case here as well. So handle the base case by returning none if the input node is none. So basically, if the input node is none, we had to return none. So in example 3, we saw, right? It was an empty graph. In that case, the input node is none. Step 2, check if the current node is already cloned in the hash map. If so, return the clone node. So once we clone the node, we don't clone the same node again. We can just return the hash map. Next, step 3. So clone the current node and store in the hash map. So basically, if the node is not already cloned, we just clone it and store in the hash map. So straightforward, right? And next is step 4. Recursively clone all neighbors of the current node and then add to the adjacent list of the clone node. So basically, we had to clone the neighbors of the current node recursively, and we have to add them to the adjacent list of the clone node. We saw, right, what is adjacent list? It's just the node and its neighbors represented in the list. That's the idea. Let's look at the code. It's very simple. So firstly, we define our recursive helper function, which is named as DFS, and it takes the current node as the input parameter. So this is the base case. So for any recursive function, remember this, the base case is mandatory, else it would give us the recursion depth exceeded error, because it would keep on calling itself without a break condition. That's why. So if not current node, return none. So basically, if the current node is none, we return the none, or we can even return the current node because it is anyways none. So that's why. And step 2, check if node is already cloned. So for that case, we just check in our hash map, right? So if current node is in cloned map, then it means that it's already cloned. So we just return the cloned map of current node. We are accessing that current node from the cloned map, and then we're returning it. So basically, I told that the key of the hash map is the node and the value is its clone node. That's why we're just returning the clone node from the hash map by using the current node as a lookup. And next is step 3, clone the current node. So basically, how can we clone the current node? So if you see the data structure given here, we have the class node defined. So we can initialize this by having the value and even the neighbors if we have the neighbors before. So by default it would be none. If you have neighbors, you can pass the list of nodes. So basically this neighbors is a list of nodes, okay? So that's why we're just passing the current node value at this time because we don't know the neighbor side. So we get the current node cloned, okay? And then we putting in our hash map, clone map of current node is equals to clone. So basically this is updating the hash map. And next is step 4 to clone all neighbors recursively. So for neighbor in the current node dot neighbors. So we're gonna explore all neighbors of the current node, and for each neighbor we just clone it and append it. So that's why we're doing clone dot neighbors dot append. So basically this clone dot neighbors is what the empty list it would be having, right? If you see here, it would be empty list. If this is the default value, if you don't pass anything. So by default it is none. So neighbors, if neighbors is not none, else none. That means that if you don't pass neighbors, it would be an empty list. So that's why we just append into this empty list. So we're using dot append DFS of neighbor. So we're gonna clone this node and append it to this node, okay? So at the end what we do, we return the clone, okay? Clone is what? Clone version of the current node, okay? So here we initialize the hash map, and this hash map would be accessed inside this function. So here in the main function we're returning the DFS of node. So basically here we're calling our helper function with a node given. So it's a DFS of node, and it would return the clone version, okay? So what are complexity? The time complexity is O of v plus c, where v is the number of nodes and e is the number of edges. Each node and edges visited once. So if you have a graph with v nodes and e edges, it's always v plus c if you do single traversal, okay? And next is space complexity. It's O of v for the recursion stack and the hash map storing the clone nodes. Because we have v nodes, right? So our recursion stack would be of length v, and our hash map is also of length v. So it is 2v actually, and 2 is ignorable in front of v, so it is O of v effectively. So I got the code ready here. Let me try running this. So it's the acceptable solution for the 3 cases. Let me try summing this. So cool, it's the acceptable solution for all the test cases and beats almost 38% of users. So now let's look into approach 2, which is a breadth first search approach. So what is the intuition here? BFS uses a queue to traverse the graph iteratively, cloning the nodes level by level. This approach avoids recursion depth issues, making it better fit for larger graphs. So basically here, instead of recursion, we will be using the iteration. So for that iteration, we would be using the queue data structure to iterate it. Okay, so basically queue, because we had to go by level, right? So in that level, we had to process the nodes in order. So that's why we use the queue here, and we always pick the first element in the queue. That's because we had to traverse the nodes level by level, right? So that's why, okay? And this also will be helpful in cases of the larger graphs. So for larger graphs, recursion might not be the better idea because sometimes there would be depth issues. That's why iteration would be a better fit in that case. So here also we use a hash map. So basically a hash map tracks the clone nodes, and the queue ensures that each node is processed only once, okay? Let's look into the algorithm. Handle the base case by returning none if the input node is none. So basically here also, if the input node is none, we don't need to process it, right? That's why we return none. And what is step 2? Initialize the hash map to store the clone nodes and a queue for the BFS traversal. And step 3, clone the starting node. So basically whatever node they give, we just clone it and add it to the hash map and enqueue it. So after adding to the hash map, we enqueue that node, okay? That way we just process its neighbors and we proceed with the next node. So that's the idea. So firstly we have to clone the given node and put into the queue, and putting in the queue is technically called as enqueue, and popping from the queue is dequeue, okay? So in step 4, we dequeue nodes one by one, cloning their neighbors if not already cloned, and add the cloned neighbors to the adjacent list of the clone node. Basically here we process the nodes one by one from the queue by dequeuing it, and then we clone their neighbors. So for a given node, we clone their neighbors. For example, if the one has neighbors 2 and 4, we clone 2 and 4 for that, okay? So if we clone these neighbors if not already cloned, okay? So basically we ensuring that we visiting all nodes and edges only once, okay? That's the idea, guys, okay? So let's look in the code. It's very simple. So firstly, it's a base case if not node, return none. So here, as I mentioned before, we can return even node here because node is none in that case, okay? In step 2, we insert the hash map and queue. So here we just insert the hash map with the node value. So we have the given node. For the given node, we're coding that node by passing node.value into the node. So we saw, right, if we pass this node.value, it would initialize the node with the given value and the empty list of the neighbors, okay? And next we are initializing our queue. So for this we are using the deck from collections. Here with the deck we can access the first most element or the last most element. It's a double-ended queue, right? So it would have 2 pointers, okay? But we would be using only pop left because we want the first node, right? We have to go by level. That's why we are accessing the first node. So first in first node way, okay? And here this deck is initialized with the given node. Next is to process the nodes in the queue. So while queue, that means why queue is not empty. Okay, till the queue has some nodes, we have to process it. Okay, and first step is to process the first element in the list. So that's why we're using the pop left of that queue. Okay, so this is defined in the deck. Okay, and then we get the current node. So for neighbors in the current node neighbors, and if neighbor is not in the clone map, so here we're ensuring that we are not cloning the neighbor again. Okay, so in that case only we clone the neighbor by using node of neighbor.value, and then we store it in the clone map of neighbor. Okay, our next step is what we have to put this neighbor into the queue. So basically we are processing level by level, right? For that case we have to put this neighbor into the queue. That way it would help us to handle this neighbor in this next iteration from the while loop. Okay, and next we have to add the clone neighbor to the adjacent list. So here we have the clone map of current node dot neighbors dot append. Okay, so basically what we are doing, it's not complex. So for a given node we're getting the neighbors, and then for that neighbors it would be an empty list initially, right? So we're just appending the cloned neighbor for that. So here with the help of the hash map we are ensuring that each node is cloned only once. That's why we are checking here if neighbor is not already in the clone map. And what we are doing, we are accessing the neighbor from the clone map. Okay, so basically we just appending the neighbors to the current node. Okay, that's the idea, guys. That way we just clone the node and its neighbors. Okay, and at the end we just written the clone start node because we had to return from the start node only, right? So they gave some start node and we had to return from the start node only. So here the node is what the start node, right? So we just written the clone map of start. What are complexes here? This time complex is O of V plus E, where V is the number of nodes and E is the number of edges. Each node and edge is processed once. So basically it's the same story here. We are processing each node and edge only once. That's why it's O of V plus C. And the what is space complexity? It is O of V. This is for the queue and the hash map for storing the clone nodes. So queue takes the V space and hash map takes the V space. So total it's 2V, but 2 is negligible when compared to V. So that's why it's O of V effectively. I got the code ready here. Let me try running this. So this accepts solution for the 3 cases. Let me try summoning this. So this accepts solution for all cases and beats almost 29% of users. Cool, right? And just to wrap on solving the clone graph is 2 different approaches. If you found this breakdown useful, drop a comment below and share your thoughts. Don't forget to like the video, spread the word to your fellow coders, and hit the subscribe button for more in-depth coding tutorials. Also, do follow on Instagram for the latest updates. And if you're looking for resources or have some doubts and want to discuss, join our Telegram community. See you in the next one.